Okay, let's continue with a talk by Mauricio Che, which is now in Durham University, and he will speak about Gromov-Hausdorff theory for some guys there. Please, Mauricio.
Thank you very much, Oscar, for the introduction. And thanks to all the organizers for the invitation to give a talk. By the way, can you hear me fine? Is that okay?
Yeah, we can hear you okay.
Okay, perfect. Okay. Yeah, thank you very much for the invitation. It's an honor for me to give a talk in this event. So yes, I will talk about Gromov-Hausdorff theory for metric pairs and metric tuples. This is based on a collaboration with Andrés Ahumada Gómez, who is, I presume, in the in-person audience. So this is a work in progress, but we are planning to upload a paper to the archive soon, so we'll keep you posted. So let me give an outline of the talk. First, I would like to recall some basic notions of the classic theory of Gromov-Hausdorff distance and Gromov-Hausdorff convergence. Then I will move on to define what is this Gromov-Hausdorff theory for metric pairs and tuples. I will define basically a class of objects that we call metric pairs and tuples, to which we extended this the theory of Gromov-Hausdorff distance and convergence. I will focus on a particularly important theorem regarding the Gromov-Hausdorff convergence, which is the Gromov precompactness or compactness theorem. It has been mentioned in previous talks because we extended that result to this setting of metric pairs and metric tuples. I will sketch the proof of that and the proof of other results that are useful to prove the precompactness theorem. And I will finish with mentioning some applications and some open questions that we might tackle in the future. So the classic Gromov-Hausdorff theory basically is a paradigm or a perspective that we can use to study the geometry of metric spaces, where instead of looking at individual metric spaces separately, we think of the whole class of metric spaces or large classes of metric spaces, and we try to understand the geometry of such classes. Right? In order to do that, we define a distance between metric spaces. So that is what the Gromov-Hausdorff distance is. It gives us a way to distinguish metric spaces quantitatively, to tell how different two metric spaces are, how far from being isometric they are. It also gives us a notion of convergence of metric spaces. And this is particularly important because, well, at least with respect to the main topic of the conference, which is Riemannian geometry, because limits of certain sequences of certain classes of metric spaces, in particular sequences of certain classes of Riemannian manifolds, have been widely studied because they turned out to have nice geometry. To give a couple of examples, we can think of Alexandrov spaces or RCD spaces, which also have been mentioned in previous talks in the conference. And these spaces arise naturally as limits of manifolds with certain conditions on the curvature. I'll not really say too much about these, but that's to give certain motivation to study this notion of distance and convergence. So to be more precise, what one does first is to define the Hausdorff distance between subsets of a given metric space. If you have a metric space Z and two subsets A and B, then the Hausdorff distance is the infimum of positive epsilon, such that A is contained in the epsilon neighborhood of B, and B is contained in the epsilon neighborhood of A. Basically, the whole set A is close to the set B, and the whole set B is close to the set A. Right. This defines really an extended pseudometric on the power set of Z. If we consider all subsets of Z, this is not really a metric. But if we restrict to closed bounded sets, then this actually defines a metric. And one can study like the geometry or the topology of this class of closed bounded subset of Z. As for example, we have the following implications. If Z is complete, then C of Z is also complete. If it is compact, then C of Z is also compact. And we should keep this in mind because these implications, we can think of them as toy results that then can be generalized when we consider the Gromov-Hausdorff distance. So now, Gromov-Hausdorff distance, as I said before, is a distance between metric spaces, not between subset of a metric space. So in order to define such thing, let's think of two metric spaces, X and Y. And what we do is we would like to find some larger space that contains them, and then use the Hausdorff distance in that larger space. And the natural choice of a larger space is the disjoint union. So we consider the disjoint union, and we say that a metric on that disjoint union is admissible if when restricted to X is the metric in X, if when restricted to Y is the metric in Y. The Gromov-Hausdorff distance is defined as taking such admissible metrics, taking the Hausdorff distance between the copies of X and Y that I have, the disjoint union, with those admissible metrics, and then taking the infimum over those Hausdorff distances. Yes, and then, as I said before, this also gives us a notion of convergence. We say that a sequence of metric spaces Xi converges in the Gromov-Hausdorff sense, or is Gromov-Hausdorff convergent to a metric space X if the distances converge to 0, right? And we write something like this. Okay, so yes, this thing defines a metric or a distance function between, to be more precise, between isometry classes of compact metric spaces. And this is because this is well defined for compact spaces, but not really for non-compact spaces, because if we have a non-bounded metric space and a bounded metric space, then the distance will be infinite. So we consider for now only compact spaces. And it is defined on isometry classes because, I mean, this has the triangle inequality, it is symmetric, it is non-negative, and it is 0 if and only if the two spaces are isometric. So once we identify isometric spaces, we get a proper, an honest distance function. So regarding the convergence, which I said that is very important thing, there are different ways to understand the Gromov-Hausdorff convergence or to formulate it. One of them is by considering almost isometries, and that is the content of this proposition here. It says that a sequence is Gromov-Hausdorff convergent to some metric space if and only if there is a sequence of positive numbers that converge to 0 and a sequence of maps that are not necessarily continuous and that are almost isometries, in the sense that are maps between Xi and X. They are almost isometries in the sense that they almost preserve distances. That is the meaning of this first inequality. And they are almost surjective. That is the meaning of this second condition here, because this condition means that for any point in X, there is some point in Xi such that its image, Pi, under Phi, is close to the point we started with. It's at most to a distance epsilon I. So this is why I call these things almost isometries. There's yet another way to formulate the Gromov-Hausdorff convergence, and this one is in terms of nets. Let me recall what a net is. If you have a metric space, we say that an epsilon net of that space is just a set of points in the metric space, such that if we take epsilon balls around those points, all those balls cover the whole space, right? So the formulation using nets of the Gromov-Hausdorff distance, Gromov-Hausdorff convergence, sorry, is that a sequence converges to a space X if and only if, again, we have a sequence of positive numbers that go to 0, and for each I, we have an epsilon I net in Xi, an epsilon I net in X, both have the same number of points. And if we compare the distances of points in the first net with the corresponding distances of points in the second net, that is what we are doing here, then they are very similar. They differ at most by epsilon I. So one can think of this as we can recover the Gromov-Hausdorff convergence by looking only at finite sets of points, right? Well, finite and very dense sets of points in xi and finite and very sets of points in x, right? That's what we have here. Okay, now these epsilon nets are very important, and regarding this concept, you can define the covering number of a given compact subset of a metric space and some parameter epsilon. The associated covering number and epsilon A is basically the minimum number of points that we need in A to have an epsilon net, right? This is what we have here. Then if we now look at a collection of metric spaces, another notion regarding the epsilon nets is the notion of uniformly totally bounded. So we say that a collection of compact metric spaces is uniformly totally bounded if first the diameters of elements in the collection are have total uniformly bounded diameter, and secondly that the covering numbers are also uniformly bounded in the sense that for each epsilon there is some uniform bound for the covering number of elements in the collection calligraphy X. Okay, now that is enough to formulate the compactness theorem that I mentioned before. And this is basically a characterization of pre-compact collections of metric spaces in the Gromov-Hausdorff topology. And it says that such collection of compact metric spaces or isometric classes of compact metric spaces is pre-compact with respect to the Gromov-Hausdorff distance, if and only if it is uniformly totally bounded in the sense of the previous slide. And just to give you examples of pre-compact classes of this kind, and which are relevant for the Riemannian geometry, precisely, are the following. Fix a natural number n, a real number kappa, and a positive number d. Then if we consider the class of Riemannian manifolds with dimension equal to n, sectional curvature bounded below by kappa, and diameter bounded above by d, that is a pre-compact class of metric spaces in the Gromov-Hausdorff topology. And the same happens if we instead consider the Ricci curvature bounded below, right? And as I said before, the limits of these classes of sequences of elements in these classes of spaces give Alexandrov spaces and RCD spaces, which are these metric spaces with synthetic notions of curvature bounded below. Right? Okay, now let's move on to a more general setting. What if we now look at the non-compact metric spaces? As I said before, the Gromov-Hausdorff distance in principle is not well defined. So what we do instead, we look at intermetric spaces, that is an ordered pair of like this, where X is a metric space, A is an element in X, and we also ask that the metric spaces we consider are proper in the sense that they satisfy the Hein-Borel theorem. That means that closed and bounded subsets of X are compact. We need that condition in order to do any kind of Gromov-Hausdorff theory here. And we want to define the convergence of such objects. Morally speaking, what we do is we say that a sequence of point-metric spaces converges to a point-metric space if for larger radii, if we consider balls centered at the distinguished points in the sequence and the corresponding balls centered at the distinguished point in the limit, they get closer and closer. We formalize this in the definition here, which I think it's most people in this business is familiar with this notion of convergence, I think, which is really just a formalization of what I mentioned before. We say that the sequence is Gromov-Hausdorff convergent in the pointed metric sense if there are epsilon I converging to 0 and Ri converging to infinity, which is these are the radii that I mentioned before, and sequences of maps, not necessarily continuous again, defined on the corresponding balls of radii Ri to the limit space that are almost pointed isometries, in the sense that they almost preserve the distance, like in the first, item. They are almost pointed maps, and they are almost surjective. That's the meaning of the third item here. And then, in that case, we denote the convergence like this. We use this notation here. Okay. Something that I think not many people are quite aware of, but I mean, it is for a good reason, but from what I gathered talking to people and asking if they are new about this, there is also a notion of distance between pointed metric spaces that metrizes the previous convergence. And in order to define such distance, consider two pointed metric spaces, xa, yb, and some positive epsilon. So now we again look at the disjoint union of the spaces, but now we talk about epsilon a, b admissible metrics on the disjoint union, which are basically admissible distance functions in the disjoint union, such that they satisfy these two conditions. The distance between a and b is less than epsilon, and a large ball around A is contained in a small neighborhood of Y, and the same with B and X. Okay? It turns out that using these kind of admissible metrics, we can define a distance function between pointed metric spaces like this. We take the infimum of epsilon such that there exists epsilon AB admissible metrics, and we take the minimum with some positive number, because this infimum really could be infinite, okay? But when we take this minimum here, then this function is finite, and it defines a metric in this setting. Well, a metric between isometric classes of pointed metric spaces, and this actually goes back to Gromov's work. But as I said, I think not many people are aware that there is this distance, because really what most people do is work with the convergence instead of the distance. We are mostly interested in the convergence of things in this way of thinking about metric spaces, rather than in the distance. But well, it's interesting to know that there is a distance that metrizes the convergence, as in following proposition, right? It turns out that the convergence of a sequence is equivalent to the convergence of this distance to 0. Now, there could be different ways to try to define a distance or a notion of convergence of pointed spaces. And an alternative way to do that is by trying to define first a Hausdorff distance between metric pairs contained in a given metric space. And we can do this in the sort of obvious way by defining the Hausdorff distance between such pointed spaces as the Hausdorff distance between the sets A and B plus the distance between the points. And then we could define another Gromov Hausdorff distance between these two guys by taking the infimum of all the pointed Hausdorff distances of these guys inside the disjoint union. Now, this only makes sense, or is only finite, when the pointed spaces are compact, so we cannot use it for non-compact spaces in principle, but we can sort of use it to describe the convergence of pointed metric spaces, not necessarily compact, but proper. In order to do that, or what we can say is that if we know that under this previous distance, I mean this one, the balls centered at distinguished point in the sequence converge to balls centered at distinguished point in the limit for any radii, any radius, then that implies that the sequence converges in the original sense of convergence of pointed spaces. In addition, if the sequence elements in the sequence and the limit are length spaces, then the converse also holds. That means that in the setting of length spaces, the convergence that I defined earlier is equivalent to this convergence for all radius. Okay. The reason that in general the converse doesn't hold if the spaces are not length spaces. By the way, well, I think I can assume that everyone knows what a length space are, but basically are these spaces where you can approximate distances using lengths of curves. Well, anyway, if a space is not a length space, in general, what happens is that the closed balls do not behave well. And we can see this in very simple examples. Consider the sequence xn given by 2 points, the point 0 and the point 1 plus 1 over n, with the distance of the real line restricted, right? And consider the point an, which is the 0. Then the sequence converges in the sense that I defined some slides before, using the approximations, the almost isometry, sorry, to the space which is just 0 and 1, and where the distinguished point is 0. However, if we look at the unit balls around the distinguished point around the 0, in the elements of the sequence, since we are considering the restricted distance, these balls are simply only contain the center of the ball. I mean, only contain the 0. Whereas the unit ball in the limit is the set 0, 1. And clearly, this constant sequence 0, 0 does not converge to this thing. So this is a silly example of why we need the length condition. Okay. Now, regarding the compactness theorem in this setting, we need to define the analogous definitions of the uniformly totally bounded collections of metric spaces. In this case, uniformly totally bounded in the pointed sense means that a collection of pointed metric spaces satisfying that condition means that the covering number of balls around the distinguished points is uniformly bounded with respect to epsilon. I mean, yeah, it's uniformly bounded. And then it turns out that this is enough to characterize 3 compact classes of pointed metric spaces. So a class of pointed metric spaces will be precompact with respect to the Gromov distance, if and only if it is uniformly totally bounded in the pointed sense. Actually, I would like to mention now a couple of results that imply the compactness theorem. First one is that whenever we have a sequence of metric spaces that satisfies certain condition, like this one, then that sequence converges to something, and we can realize the convergence of such sequence inside some larger space. That's what we have in this theorem here. We can find some locally complete metric space and some subset of the completion in some point in that subset, such that each element of the sequence isometrically embeds here. The completion is a proper space, and we have convergence. We sometimes call this result the embedding theorem. And we also have the following result that the space of pointed metric spaces with this distance, Hausdorff distance, is a complete metric space. We have the same results also for the Gromov distance in the case of compact metric spaces. And basically, once we prove the pointed case, that implies the corresponding results in the case of compact metric spaces. These really, I don't know who to attribute these results, but a very good summary of these theorems can be found in this paper I'm citing here. I will mention the reference later. Okay, so now let's move on to what I mean by metric pairs and tuples and the Gromov-Hausdorff theory on those things. Very simple. A metric pair will be simply an ordered pair of this form, where X is again a proper metric space and A is a non-empty closed subset. So basically we change points for closed subsets. This kind of objects might be used to study certain situations or certain phenomena where distinguished subsets arise in a natural way. For example, if one is studying manifolds with boundary, or if one is studying stratified manifolds, or if one is studying, I don't know, manifolds with some action, and you're looking at points with certain kind of orbit. So yeah, I mean, there could be many other examples that I don't know, but I think it's somehow a situation that might appear in different places. And the idea of considering these metric pairs and considering the Gromov-Hausdorff convergence of such things came up when in another collaboration with Fernando Galas Garcia, Luis Guijarro, and Ingrid Membrillo Solís, where we were studying certain geometric construction coming from the topological data analysis, which involved metric pairs. And we observed that this construction was continuous with respect to this convergence. I will say more in a moment, but we have this definition of convergence of metric pairs, and it's basically a mild generalization of the convergence of pointed metric spaces. He said that a sequence of metric pairs converge to a metric pair if there are sequences epsilon I that go to 0, Ri that go to infinity, such that we have almost relative isometries, in the sense that they almost preserve distances, they're almost surjective, and the image of the distinguished set AI is very close to this distinguished set A with respect to the Hausdorff distance in the limit space. And in that situation, we write this notation. Again, we can also define a distance function by considering now epsilon AB admissible map and metrics on the disjoint union of X and Y, and then taking the infimum of such epsilons, the minimum of this and some constant, and then we have analogous results. This defines a function between isometric classes of metric pairs. This metric distance metrizes the convergence. And we also try to approach this idea of convergence by the in an analogous way as we did in the pointed case. We could define a Hausdorff distance of pairs in a given metric space like this. Here, I made a mistake. This should be the Hausdorff distance of A and B. And we might define the Hausdorff distance or another Hausdorff distance between metric pairs as the infimum of such Hausdorff distances over admissible metrics in the disjoint union. And we got a similar result as we did in the pointed setting. And we get that if we have a convergence of balls in the sequence for any radius r, then the corresponding sequence converges in the previous sense. And if in addition the spaces are length spaces, then the converse also holds. And we also got pre-compactness theorems, pre-compactness theorem or compactness theorem in this setting. In this case, the characterization of pre-compact classes of metric pairs needs to define what a uniformly totally bounded class is in the sense of metric pairs. And here we combine more or less the uniformly totally bounded notion in compact spaces and the uniformly totally bounded notion in pointed spaces. Here we say that a collection of such metric pairs has this property if it has if whenever we look at the distinguished set in each element of the class, the diameter of that subset is uniformly bounded over the collection, calligraphic X. And again, we look at the covering numbers, but now the covering numbers of large balls around the distinguished sets. And we want those covering numbers to be uniformly bounded. And then we get this characterization of compact collections in this setting. Again, we have that a class of metric pairs is precompact with respect to the Gromov-Hausdorff topology, if and only if it is uniformly totally bounded in this sense. We also got analogous results to the embedding theorem and to the completeness theorem. And now I would like to give an idea of how to prove these results. Actually, I will start by showing how to prove the embedding theorem, then how to prove the completeness theorem, and then how that implies the compactness theorem. The proofs really everything that we have done is basically analogous to what one does in the pointed setting, but taking care with the compactness of the distinguished sets in the metric pair. And so I will sketch the proof now. Regarding the embedding theorem, what we do is we basically want to, if we start with a sequence that satisfies this condition here, and we want to prove that there is some larger space where this sequence is embedded into. So in order to do that, we choose positive numbers epsilon I, such that the distances between consecutive pairs is less than epsilon I, and such that the series of epsilon I is finite. We could do this because this series here is finite. So say we could consider this distance here and add some sequence of numbers that make a convergent series. And then we take admissible metrics, or more precisely epsilon I, AI plus 1 admissible metrics on the disjoint union of the consecutive sets. So that gives us like admissible metrics between each pair of consecutive metric spaces. And then we glue together all those distance functions. We glue together all those, although we consider the disjoint union of all these spaces and glue together all these distances in a natural way. And then that is our larger space, which naturally contains the copies of xi. So it's kind of what one would expect. And we define the limit space x simply as the boundary of y, or which is another way to say the completion of y minus y. Okay, so one has to look that this is non-empty and that it is a proper metric space. I mean that y, the completion of y is a proper metric space, that y is locally complete, yada yada. But I mean, this is basically construction of these sets. And finally, the subset A will be simply the set of points in this set X that are limits of sequences of points in Y, such that each point in the sequence is in the corresponding subset AI, and such that the consecutive distances between, the distance between consecutive points in the sequence are less than epsilon I. And well, okay, yeah, one has to check that these satisfy the condition, but this is the way to construct that limit space. Okay, now for the completeness theorem, what we do is, okay, we want to prove that any Cauchy sequence of metric pairs is convergent, right? So we start with a Cauchy sequence, and we always, in that situation, we can always find a subsequence that satisfies this condition, right? And this is just really because of the definition of Cauchy. And then what we do is we apply the embedding theorem to this sequence, to this subsequence, sorry. And this gives us that the subsequence is convergent, But then if we have a Cauchy sequence with a convergence subsequence, then that means that the original sequence was also convergent. That's how one proves the completeness. It's pretty straightforward once you have the embedding theorem. And finally, regarding the pre-compactness or compactness theorem, remember, it is a characterization of pre-compact classes. So first, we will start with a class that we already know is pre-compact, and we want to prove that it is uniformly totally bounded on the sense of metric pairs. So we start with the class that is pre-compact, and then being pre-compact, well, it means that any sequence has a convergence subsequence. But then it also implies that this class is totally bounded. Not uniformly totally bounded, just totally bounded in principle. And that means that for any epsilon, we can find some finite set of metric pairs that make up an epsilon net of the given collection X, calligraphic X. And then what we do is we define some number, but here let me first mention what these numbers here are. P of epsilon y, where y is some metric space or subset of a metric space, is the maximum, basically is the maximum number of disjoint epsilon balls that we can pack inside the set y. So that is why we use the notation P, because it stands for packing number. Okay, and then it turns out that, well, okay, we can do this. We can look at the packing numbers of epsilon and the large balls around the distinguished sets AI, where I goes from 1 to n. So we look at these sets here. We look at the subsets AI and look at these balls around them and the packing numbers. We take the maximum of that. And then the thing is, we can actually compare packing numbers and covering numbers. I will not do that very explicitly, but by doing so, it turns out that these, well, and using the fact that the calligraphic X class of metric pairs is pre-compact, we can prove that this number new epsilon works as in the definition of uniformly totally bounded metric pairs. That is, this new epsilon is an upper bound for the covering numbers of these kind of things, which is precisely what it means to be uniformly totally bounded. Now, if we assume that we have a uniformly totally bounded collection of metric pairs, and we want to prove that it is pre-compact, so we take some sequence of elements in that class, and we want to prove that that sequence has a convergent subsequence, right? So, but what we can do with this sequence and using the hypothesis is that actually we can assume that that in this sequence, these covering numbers are constant. And why can we do that? Well, we can do that because uniformly totally bounded means that these covering numbers are uniformly bounded by some positive number. But then, if we look at that positive number and all the integers that are between 0 and that number, that is a finite number of integers, right? And those integers do not depend on the elements of the collection of spaces. It just depends on epsilon, okay? So if we look at the sequence and if we look at these covering numbers associated to epsilon and these balls, we have an infinite number of elements in the sequence, which have for which these covering numbers can only take a finite range of numbers. So there is at least one element in that finite set of integers that repeats infinitely often. So we can pass to a subsequence where that number is constant, okay? And we call that number n epsilon, because again, it only depends on epsilon. Then what we do is I mean, what is the meaning of this? What does it mean that these spaces have a constant covering number? Well, it means that for each one of these, well, here there is a typo here. This shouldn't be the pair XI-AI, it should be the ball around AI. There is a finite epsilon net of the ball around AI, and all those epsilon nets have the same number of points, right? Have n epsilon points. That is the meaning of these being constant. I'm just interpreting the definitions. And then again, we have epsilon nets for each one of these balls. And here we use the fact that all these subsets AI have bounded diameter, because since these AI have bounded diameter, the balls of radius 1/epsilon AI around AI also have bounded diameter. It will be basically the diameter of A plus 2/epsilon I over epsilon, sorry. That is an upper bound for the diameter. And then if we look at the distances between points on each one of these nets, all those distances are in this are less than that uniform bound. So what we can do is, or what we do now is, we have an infinite sequence of epsilon nets. The distances between points in each net are within one fixed interval, and each net has the same size, has the same number of points. So basically, again, by using this sort of pigeonhole argument, we can say that there is an infinite, there is a subsequence such that the distances between pairs of points are located very close to each other. Basically, we partition this fixed interval given by the upper bound of the diameter, and with the same number of subintervals as the number of possible distances between elements of the net. And for infinitely many elements of the sequence, those distances will be in the same subinterval. That's more or less the idea, but yeah, the point is we can take a subsequence where these nets are very close to each other. But remember what I said in some of the first slides. Whenever we have epsilon nets in a sequence where, and these epsilon nets have the same number of points, and the distances are very similar to each other, then that means that the sequence converges. So that's in this case, we don't get the sequence converges, but what we get by considering epsilon nets is that the sequence is Cauchy. And since we have proved that the space of metric pairs is complete, then we get that this sequence is not only Cauchy, but it is convergent. Okay. Now, regarding metric tuples that I mentioned, I mean, that are in the title and that I have mentioned before, really is just the same story. But now, instead of having a metric space and considering a distinguished subset, we now consider chains of subsets. And that's what we call a tuple. And then again, we can define convergence in the setting in the natural way. We can extend the definitions in the natural way. Now, we say that a sequence of tuples converges to a tuple in the Gromov sense if we have epsilon isometries in the tuple sense, which means that they almost preserve the distance, they are almost surjective, and each one of the elements on the tuple, well, on the tuples in the sequence, are mapped to sets that are very close to the distinguished set in the limit tuple. Okay, that's just like a natural extension of the definition. All right, now I would like to finish with some applications of this framework, not really applications of the theorems that I mentioned, that I just showed the proofs, but applications of this language. And here I'm not really saying anything very deep. It's just that we can formulate some known facts in terms of this. First, regarding how we came up with this idea of metric pairs and the convergence of metric pairs, I'd just like to mention that, again, this came from a collaboration on a project that has to do with a geometric construction in the topological data analysis. And that geometric construction is that of persistence diagrams. I will not say really the motivation of this, but given a metric pair, we say that a persistence diagram on that metric pair is certain equivalence class of countable multi-sets of points in X, where we identify such multi-sets of points whenever they differ only by points in the distinguished set A. This really is a generalization of what a persistence diagram is in topological data analysis. And the thing is, we can endow the set of persistence diagrams with some metric that in the jargon of topological data analysis is called the bottleneck distance. This is really a pointed pseudometric in this space of persistence diagrams, which we denote like this. And in this collaboration, in this previous paper I mentioned before, we proved that this construction, the correspondence that sends each metric pair to this pointed metric space, it is sequentially continuous with respect to the Gromov-Hausdorff convergence of metric pairs and the Gromov-Hausdorff convergence of pointed metric spaces. Well, joining this paper with the work that we've done with Andrés, we actually get continuity, not only sequential continuity of this construction. Okay, and this was one of the goals of studying this notion of convergence. And finally, and I will be very sloppy here, but you can ask questions later. We apply this framework or this language to write some things in terms of convergence of tuples. The first application is just that has to do with extremal sets in Alexander spaces. And there is this theorem by Petrini that if we have a sequence of Alexander spaces that converges to an Alexander space and is a non-collapse sequence, and if we take extremal sets on each element of the sequence, then these extremal sets converge to some subset of the limit, then that subset is also an extremal set. And what we did here is basically a tuple version of this, where we consider tuples of extremal sets, and then the limit is also a tuple of extremal sets. That's basically it. Then the second application of this is based on a theorem by Fukaya regarding the equivariant Gromov-Hausdorff convergence. And the original, or well, the theorem that I'm alluding to here is that whenever we have a sequence of G spaces that equivalently converge in the Gromov-Hausdorff sense, then the quotient spaces with the action or converge to the quotient space. And well, we got a tuple version of that, where if we consider a sequence of subgroups of the group acting on the sequence and then limit, and then we can look at the sets of points such that the type of orbit is given by those subgroups. And then that gives us tuples. And then those tuples, the quotients of those tuples by the action also converge to the corresponding quotient and the limit. And finally, we also apply this framework to the setting of stratified manifolds and proved a tuple version of the Grove-Petersen-Wood theorem about the finite number of topological types of stratified manifolds. Okay, and yeah, if you have any question about this, please ask me once we finish the talk. And I want to finish now with some open questions or questions that might be interesting in this using this language. What other applications do we have? Maybe if we consider manifolds with boundary, as I mentioned earlier, can we say something about these kind of manifolds if we impose certain control on the geometry or restrictions on the curvature or something like that? Can we say that such classes of manifolds are precompact, for example, in the sense of tuples or in the sense of pairs? That is one question. Another question that might be interesting is what other properties do these spaces have, the spaces of metric pairs and metric tuples with the Gromov distance? And finally, is it possible to extend these or to generalize it even further? Maybe we could consider, instead of finite tuples, maybe infinite tuples, like sequences of nested spaces. And what can we say about them? Yeah. So that's all I wanted to say, and thank you very much for your attention. Here are some references. Thank you very much.
Thank you so much, Mauricio. Are there any questions for this Duranguense pair here in the audience? Yes.
Hi, Mo. So, have you also extended the equivariant Gromov-Hausdorff distance for metric tuples?
Not really. And in the theorem that I mentioned here, probably that's why you're asking about that. What we do is we have a equivariant convergence sequence, but not any sequence. We are considering only manifolds with curvature bounded below, and where the limit is some Alexandrov space with which also has an action. And also this convergence is non-collapsed. So this is a very, very particular case, just where we could manage to say something. And the thing is, in this setting, we know that we can take this equivariant approximations, which is in something that one has in the definition of equivariant convergence. We can make them to be equivariant homeomorphisms. And then we use that in order to send invariants, well, sets of the same orbit type to sets of the same orbit type in the limit. It's not really something very deep because we are using this stability theorem in the, well, equivariant version of the stability theorem, which is work by John Harvey. Yeah.
Okay, thanks.
More questions? Comments? No? Not? Let's thank Mauricio again.